In fluid mechanics, when we talk about turbulence, we like to say things like, turbulence is one of the greatest unsolved problems in physics. That's a lot of razzle-dazzle. Turbulence is definitely mesmerizing and complex, but that's not a reason not to get interested into it. Let's check it out together. One of the first things that should strike you when you look at a turbulent flow is that it's complex and mesmerizing. And today I want to focus on learning how to recognize whether a flow is turbulent or not. The first thing that you might be thinking is that there's some random aspect to it, meaning there's an overall average flow, but if you take any specific point in space, it's hard to predict in advance what the velocity will be at an exact moment later on. Let's start with kinematics. Kinematics is the description of movement of things without focusing on the causes or the consequences just yet. I said earlier that often we think that turbulence has some kind of a random component to it, and that's not correct. The precise term that we're looking for here is that turbulence is chaotic. Now, chaos and chaotic has a different meaning in the common language than it has in physics. In the common language, a teacher might come to you and say, my class with the 7th graders this morning was chaotic. But that's not what we mean when we say chaotic in physics. In physics, one of the best ways to explore the notion of chaos is with this extract from a really cool documentary by Jos Liss, Etienne Guis, and Aurélien Alvarez. And here we see two billiard games which are exactly identical except for one tiny difference, which is the green ball on the bottom left, which is placed slightly differently. What happens when we play the both simulations? What happens is basically nothing is very much different. If you focus on the white ball and look at its trajectory, there's really not much of a difference at all until you reach some point where something starts to change. And we notice now that a tiny change in the initial position of the green ball results in a very large divergence in the movement of the white ball later on. Chaos in physics, then, means that a minute change here, now, results in a large change in the exact configuration everywhere later. Equally important to state is also that it doesn't change the overall condition. Right? So if you look at both billiard games from far away, they look just exactly the same. Just if you look close, you will see that the position of the balls is different. In a way, then, it's not that the butterfly's wings cause a hurricane later. It's more that the exact way in which the butterfly flaps its wings right now ends up determining the exact time at which the first drop of water will fall on the hood of the blue car as the hurricane approaches later on. Yes. So a minute change now affects the exact configuration later. Another way to see it is with this thought experiment. Imagine that you plant a tree. It's a small tree now. You put it in the earth, and it's about this size, and you know the exact configuration of every leaf and every piece of earth. And you ask yourself the question, today, in 10 years, exactly, what is this tree going to look like exactly? And we have great ways to do this on average. So if you tell me the latitude, the geography, I will be able to tell you the diameter of the tree, the diameter of the trunk, its height, and so on and so forth. But in detail, that becomes impossible, because to know the exact configuration of every leaf and every branch of that tree in 10 years, you need to know the whole process. You need to know at which time exactly which bug landed on which leaf and what was the temperature on that day. In fluid mechanics, it's the same thing with turbulence. We are, in general, not that interested in knowing every detail of the turbulence, and instead what we want to know is its general overall properties. There are two ways then to deal with turbulence in general in physics and engineering. The first way is to describe it in detail. So I'm describing the velocity, the position of every fluid particle in the flow, everywhere, all the time. There are two problems with this. The first is that it's a lot of data. So even if you have a big computer, you are presented with a lot of different little velocities that are hard to make sense of and hard to explore and to analyze. And the main problem, the second problem, is that it's extremely expensive to obtain. Without loss of generality, because it depends on the details, we're talking about months of calculation for just a few seconds of airflow around the car, for example. So most of the time we can't afford to do that, and we use the second approach, which is to describe turbulence in bulk. That's to say, I'm going to divide my volume of interest in boxes, in voxels, I guess you could say, and in each of those boxes I will describe the average flow and then some bulk property for turbulence without describing its every detail. So we'll be looking at things like intensity or percentages and so on and so forth. Besides kinematics, the other important aspect of turbulence is energy. And the key sentence to remember here is that turbulence is dissipative. And by this we mean that turbulence needs a source of energy. It doesn't just happen magically all by itself, spontaneously. It is supplied with energy by something. Or that something is very often shear or pressure created by a solid object inside the fluid. Turbulence stops if it's left to itself. It receives energy and it dissipates this energy, so that if you leave the flow to itself, eventually turbulence dissipates and nothing is left. And in the process, it has taken large structures that it breaks down into ever smaller structures, right down to the movement of molecules, so that it ends up dissipating large scale, macroscopic, measurable forms of energy like pressure, velocity, and so on and so forth, and it reduces that down to an increase in internal energy, which is measurable as temperature. Beware, though, that the increase in temperature that's created by turbulence is most of the time completely unmeasurable. This is because the heat capacity of fluids is extremely large, and the amounts of energy absorbed by turbulence are comparatively small, so that you're talking about 0.000 something degree of increase in temperature, which is easily overwhelmed by other heat transfer phenomena. Coming back to our beautiful turbulent river flow seen from above here, then the source of energy in this case is the shear of the water over the rocky bottom surface that we can just make out below the water. This provides it with a source of energy continuously to feed and maintain the turbulence. If you remove this, for example, if you let the river flow into a calm lake, then the turbulence completely disappears. Be careful, however. A turbulent flow is always a complex flow, but the opposite is not true, right? So this is here quite a beautiful and relatively complex flow, but it's not turbulent. And you can see this because you will make out two main groups of frequencies in this flow. One group is the big waves, which are low frequency, slow movement. And on top of that, superimposed, is the small waves with a relatively high frequency on top of that. And these two groups are not interacting with one another, meaning the large waves do not become medium waves that become small waves. They just pass, and actually waves, surface waves on the water like this can travel for miles undisturbed. You recognize turbulence then in that it is chaotic, meaning a tiny change at the start ends up having a big effect on the downstream conditions. And in the fact that you see many structures of all kinds of shapes and especially of all kinds of sizes. So large structures become smaller, medium structures that become smaller and ever smaller, right down all the way to the movement of the molecules through dissipation. Let's sum up then. How do you recognize turbulence? Well, the first thing to keep in mind is that turbulence is not magic. It may sound funny to say, but I think it's important to state it explicitly, because in fluid mechanics we often tend to shove the topic down the line, and which kind of feeds a mystery around the topic. That's too bad. Turbulence is not magic. It's completely predictable phenomena, and we master it very well. You will recognize turbulence in that it's chaotic motion, meaning a tiny change in the initial conditions will result in a relatively large change in the specific configuration later. You will recognize turbulence in that there are structures of all sizes. Large structures become medium, become small, become very small structures progressively. And you will recognize turbulence in that it's dissipative. It requires energy to happen, and it will stop if it's left to its own. We'll come back many times to the topic of turbulence in the coming videos, but I think that's a good first approach of the topic. I hope you'll be able to make good use of it, and I'll see you in the next videos.
Hi, I am Olivier Klein and I'm recording a video course in fluid mechanics. If you find this video useful, check out the rest of them at learnfluidmechanics.com. I hope to see you there. Take care.